Alright, I have just started the streaming, so that should pop up in 1 second or so. There you go. Alright, so streaming is on. I'm gonna close that window, and what you're seeing here is not for this class. This is for CISW410, which is a web scripting class that I picked up right around week 4 of the semester, which is kind of the busiest time, one of the busiest time of the semester. So anyway, I finished grading. Oh, let me see. Right. Yep. I need a screen share on this side too. There we go. Not that the screen right now is actually of any use to you guys, unless you want to learn how to do Node.js and Express scripting. It's actually a fun class in its own way. This class is fun too. It's a lot of fun for me. So to get your aggregated score, I'm gonna have to enter that into Canvas, which I have not done yet. I was hoping to be able to distribute your grades, using the spreadsheet system, and most of you got it. As I was running the script at one point, it came back with an error and said that I have run out of quotas to use a particular API, which is the API to send email out. That had never happened before, and I have had larger classes than this one, and I have never had this problem before. So it has to be something new, some new quota that they have decided to implement or enforced in this system. I'll try that one more time. So some of you may be getting a duplicate email, but I'll try that one more time and see what happens. Yeah, it's not going to do it this time. Even the first person is not getting the email, so I have run out of my quota to send email out. What am I going to do, right? I mean, I am going to have to hand enter the aggregated score for the last few people on roster. I think most people on roster got their message already. It's just very few close to the end of the roster who could not get it. So, and the district is also implementing second factor authentication, which also rendered a lot of my automated scripts basically useless, because my automated scripts cannot interact with the second factor authentication. So yeah, they're trying to tie my hands behind my back and have me to do all kinds of tricks. We'll see. I can be Houdini sometimes. Alrighty, let's see, what time is it? We still got about 10 seconds, and then we're gonna get started with today's lecture, which is a continuation of the one before, so not very surprisingly. Alrighty. Alright, so let's go ahead and get started. So first thing is I'm gonna restart Logisim, because I had to restart my computer yesterday, so all my usual apps that's up and running is no longer up and running. Oh, one more thing. I forgot to mention this. So if you have your graded exam in front of you, that makes it possible for you to compute your own aggregated score. So part 1, which is the Sudoku part, is 0.6, 60% of the score of a question, and then the other parts will be spread equally, so 20 and 20% for the other 2 parts. So when you look at the first page of your of your exam, the graded one, the PDF, you see the 3 numbers. The first number, if you multiply by 60%, the second number multiplied 20%, and then the third number also multiplied by 20%. That would be the score for one question. And then the overall score is just the average of all the questions that you answer. So if you choose group A, then you'll be adding up all the scores for the 3 questions and then divided by 3. If you answer with group B, then it will be divided by 5, and if you're in group C, then it will be divided by 8. But because group C has a cap of a B, so then you have to multiply that by 0.75 as well. So that's the that's the equation that I used to come up with the aggregated score. Since you have the raw scores already, you can also do the calculations yourself. All right, so apparently there are no questions about that part, so we're going to get started with TTP again. Okay, so let me get that started. And I really hope, I do not know for sure, but I really hope that most people have a chance to play with the processor in Logisim the way that I described it on, Tuesday. Because it's rather important that you guys get used to analyzing the processor the way that I did on Tuesday, because that's how you learn how this processor works, and that's how you're going to be preparing yourself for the second exam. So I know it looks kind of daunting, but I gave you some pointers of how you can do this. You basically make an inventory of items that are quote unquote active. When I say active items, I mean things that can store data. So that would be RAM, all the registers. ROM in a certain case, in a certain sense, it's like that too, but not as much. And then the ALU is also a little bit special, because it has a lot of components inside it. But for the most part, you have to keep track of all the things that can potentially do something. I wouldn't pay as much attention to the multiplexers or the demultiplexers. They can be analyzed as needed, because when you figure out 2 things are actually active, then you want to figure out how they are connected. That is when you need to look into the multiplexers and the demultiplexers to find out how components are connected. What we'll do today is we are going to use 2 more instructions to illustrate how the processor works. And going to the opcode table, we're going to pick up LDI first, okay? Because LDI is an interesting one. This is the LDI instruction, and this is the binary bit pattern when you are working with an LDI instruction. This is the opcode. So opcode is always referring to what the processor actually sees when it is getting the instruction from RAM. So that's the opcode. The opcode in this case is 0110, which means the first hexadecimal is always going to be a 6. And then the least significant 4 bits is going to be 11, so that part has to be there. And then the XX is going to be used to specify one of the 4 registers in the register bank. So in the register bank, they're called registers A, B, C, and D, basically just a way to distinguish one register from another register. Column B tells you about the mnemonic of this particular instruction. So LDI has to be followed by a register, which is A, B, C, or D, and also followed by an immediate operand. So right here in row 3, it is explained that I specifies a constant value determined at assemble time. Okay, so it can be a literal constant, can be like 5, 6, or something like that. And then column C is interesting for this one because it tells you how it is done. Okay, it doesn't really tell you functionally what it does, but it tells you how it is done. So depending on how you want to look at RAM, some people like to look at RAM as actual memory, in which case the reference is the correct operator. Other people like to look at RAM as an array of locations, and we can address locations and we can change the addressed locations, or we can get the content of the addressed locations. Either way is okay. I personally prefer the use of dereferencing, which means I like to look at RAM as memory. But that's kind of your choice, okay? How you want to see that. Alright, so right now we see that LDI doesn't even mention I in column C. All it does is to say X, which is referring to the register specified by the first operand of the mnemonic, is getting whatever the program counter is pointing to, and then the program counter is going to post increment. Okay, you can see how the plus plus is on the right hand side of PC, which means it is a post increment operation. Post increment, in case you cannot remember what it is from CISP360, means the increment occurs after the entire expression is evaluated. Okay, so we are using the value of program counter for everything, and then after everything is done, then the program counter is incremented. Do we have any questions about how I just read the 3 entries in the opcode table? Okay, so we're good here. All right. If anyone needs more time, just let me know, okay? Because it's rather important that we learn how to interpret what column A is representing, what column B is representing, and what column C is representing. Column D is really just an English description of what it does. Okay, so typically it is helpful if you just kind of forget about which one is which one, but it's not very helpful when you want to figure out how an instruction executes. So now we go to Logisim and we try to figure out how something executes. So in order to right after means next byte. No, right after means, you'll see, okay, because when we execute the LDI instruction, you will see when the program counter increments, okay. But in okay, let me also clarify what auto increment or post increment means. I need to switch to a my mouse pad, which is down. Oh, I just got past it. Sorry. There we go. And it's not on. It's not in the region that is being recorded, so I'm going to stash it here. And by the way, this is one of the formula in the spreadsheet that I use to compute your aggregated score. That's what it looks like. Not a big deal. There we go. Get rid of it. Okay, so if you just have some kind of expression, I'm gonna say, I is j plus plus times n plus plus. Okay, I don't even care why we are doing this or what it is for. Okay, it doesn't really matter. But this really is the same thing as j I equals to j times n, and then after that we have a j plus equal to 1, and then followed by a n plus equal to 1. So these two blocks of code are identical in terms of what they do. This is basically just a shorthand of this. So are we doing okay so far, in terms of what post increment actually means? We good? Okay, excellent. All right. So now that we got that cleared up, let's find out how the processor actually gets it done. Okay, and for those of you who might want to get back to this and try to review what I just talked about, you might want to put a time mark. In other words, it's 9:09 right now, so you might want to just kind of jot down, let's say 9:10, TAC starts to talk about the execution of the LDI instruction, and I'm going to go through all the instruction cycles. That's something that we talked about on Tuesday, so you might want to also kind of bring up the notes on Tuesday so that you understand, oh, here's the fetch cycle, and here is the decode cycle, and here's the execute cycle. There are at least 3 cycles to the execution of each instruction. Alright, so now we switch back to Logisim because we are ready to execute the instruction. But before we do that, we have to assemble it first. Okay, in other words, we have to somehow figure out what bit pattern should go into location 00, which because execution starts at location 00. So we need to somehow figure out what bit pattern should go there. So let me go back to here. So I want to specify LDI register B with a constant of 56. Okay, just totally random. Okay, I picked register B just because. I picked the constant of 56 just because. Okay, so now I need to assemble this. Okay, I need to figure out what bit pattern is supposed to specify this operation. So it starts with a 0110, which is 6. Okay, so in hexadecimal this is a 6, And then we have two 1-1s. Okay, that also needs to be there. There's no particular reason other than, hey, when I was trying to code this particular instruction, that's the next constant available. And then we have register B. Register B is actually the second register, but the first register, or register A, is 0, 0, so that makes register B 0, 1. So now we can come up with the entire code of 6D. Okay, 6D specifies the LDI instruction. The thing about the LDI instruction, or any instruction that ends with an I, is that the immediate value is right after the opcode itself. So this time we have 56, which is a base 10 value, and now we need to specify that in hexadecimal, because that's how we enter values into RAM. So 56 is 48, which is a 3 times 16 plus the 8, so 38 would be representing 56. So these are all in hexadecimal, so I'm going to use 0x to emphasize that we are dealing with hexadecimal digits here. So I need to inject these 2 bytes into RAM. Okay, this one is at location 0, 0. This one is at location 0, 1. And then we also need a halt instruction. The halt instruction is easy. It's just 0, 1. So we need 0, 1 here in location 2, just so that the program will stop. Because otherwise, the program will keep going and going and going. Alright, so knowing that these are the locations we need to inject into RAM, I'm going to put it into RAM right now. And let me zoom in, because I zoomed out because we were looking at the forest, because I was trying to explain, generally speaking, how things work. But now that we are trying to track down the execution of a specific instruction, clock by clock, actually I take it back, not clock by clock, but transition by transition, because one clock consists of a rising edge and a falling edge, but I want to track down, like, this is a rising edge, this is falling edge, this is a rising edge, this is falling edge. Okay, so the first location is, okay, I'm looking on the side here, it's a 6D, specifying the actual opcode. The next location specifies the immediate value, which is 38 in hexadecimal, and that is 56 in decimal. And then the last one is a 0, 1, which is our halt instruction. So this way the program will stop automatically. Alright, and now we are ready to go. I'm just looking on the side to see if there are any questions in the text channel, and so far there are no questions. Alright, so now we are ready to start. Okay, and I'm going to do this a few times, but after these few times I'm not going to do it anymore, because the analysis of how an instruction executes is going to be the same. It's just that different components get activated, and then different multiplexers and different demultiplexers would also be configured differently in order to establish different pathways within the processor. But the process, the steps to analyze, is the same. So we always start with location 0, 0, 0 in ROM, because the microcode pointer is initialized by one of two means. The reset line resets it, but it is also reset by the most significant bit coming out of the D port of RAM. So either way we reset it. But right now, since we just started LogiSim, so it is reset to 0 by default. Location 0, 0, 0 in ROM specifies the fetch operation, and we are on the rising edge. So we are now currently doing a fetch operation. Now the fetch operation, I'm not going to do the very slow analysis like on Tuesday. So we'll just kind of go straight to the components that are active. So RAM is active. We're in reading mode, and the what specifies the address to look into RAM is the program counter. So the program counter is located here. It is going into a multiplexer. This multiplexer does not have an enable, which means it is constantly enabled. And the select is saying we are choosing input 1 to connect to the output. And here's the output. And then we can see how the output is going into the A port of RAM, which means we are now using the program counter, which is a register, to specify that we want to look at location 0, 0 in RAM. So the next question is, who is going to get the content coming out of the D port? Now there are a few things that connect to the D port, but since we did this analysis on Tuesday already, so we know it is going to be the instruction register, which already has the enable turned on. So when the clock goes from 0 to 1, on the rising edge, the instruction register is going to get whatever is coming out of the D port of RAM, which is the content of location 00, which in this case is 6D. So I'm going to type Control T on the keyboard right now, which gives me a single edge of the clock line. So right now we can see how the clock is light green, meaning it has a value of 1, and we can also see how the instruction register now has a value of 6D. The next transition is the falling edge. At the falling edge, none of the other registers would do anything except for the microcode pointer. The microcode pointer is always enabled, okay, because you can see how the EN line is connected to a constant of 1. But it updates on the falling edge. So right now, we know the next transition is going to be a falling edge. So now we need to look into how the microcode pointer is going to be updated by tracking down its D port first. So the D port is coming out of a multiplexer. The multiplexer has a select of 1, which means input 1 of this multiplexer is what is connecting to the microcode pointer's D port. And this is coming out of the adder, which is just constantly adding 1 to the microcode pointer itself. So this is an increment mechanism implemented in hardware. So all that means is at the falling edge, the microcode pointer is going to increment to 001. So here we go, Control T, and voila. The microcode pointer is now 001, which is a different location. Basically it is also sending out, different values for all of these control lines. There are 26 of these control lines. Most are going into multiplexers, demultiplexers, and registers. One is going back into here to reset the microcode pointer, which we will get to, but not yet. Alright, so on the next rising edge, we are going to increment the program counter. This is also something that we analyzed on Tuesday. So it is quite important that you kind of either jot down the notes from Tuesday or watch the video again from Tuesday if you're not quite understanding why the program counter is going to be incremented. So I'm going to give it a rising edge, Control T, and the program counter is incremented. Now, this is important, okay? This is really important because the program counter is no longer pointing to the opcode. It is now pointing to the byte that contains the immediate value. That is why the PC++ dereference is going to work. That is why this particular code is going to work, because the program counter is now pointing to the location in RAM that contains 38, which is 56 in base 10. It is pointing to the value that we want to grab from RAM and store into whatever register we want to specify. Alright, so this is really important, okay? This is really important. This is also why we have to increment the program counter as soon as the opcode is read. There's no specific name for this particular event, okay? This rising edge is just saying, hey, program counter, you don't need to point to the opcode that we have already stored into the instruction register, so why don't you go to the next location? That is what this particular transition is doing, but it has no special name. If you want to, you can count it as a part of the fetch cycle, okay? You can include this as a part of the fetch cycle if you want. Alright, so next cycle is going to be a falling edge. So at a falling edge, we know that only the microcode pointer is going to change. But this time, how the microcode pointer is going to change is different. It's not going to the incrementer. In other words, it's not just going to go to location 002, because the multiplexer has a select of 0. So that means input 0 of the multiplexer is going to be used. And this is the mechanism that I can do a hardware left shift by 4, because I am taking the entire register, the instruction register, from bit 0 to bit 7, but I'm shifting those to bit 4 to bit 11 because of the use of this splitter, okay, slash merger. What I'm specifying for bit 0 to bit 3 is just a constant of 0. So at the falling edge, all I'm really doing is to put 6D0 into microcode pointer. Okay, does everybody understand how this works? The way this works really just depends on the splitter. The splitter is the quote-unquote magic of this. Okay, cool. Thank you. All right, so I'm going to type Control T on the keyboard. So the microcode pointer will now be updated to 6D0. This is the decode cycle when we execute instructions. We are decoding it right now. All right, so Jonathan said, so instruction register goes to instruction, which goes to microcode pointer. Okay, so the reason why I cannot read directly from RAM, into the microcode pointer is because there's a reason. Oh, right, because if I did that, it would immediately change the address of the ROM, which potentially can basically pull the rug from under myself. So that's why we need a particular register to store the opcode first, and then move that into the microcode pointer. It adds one extra clock because one is changing on the rising edge and the other one changes on the falling edge, but it basically makes sure that everything is lockstep at this point. And then Richard is typing something. So it's kind of like a buffer. Exactly. It's a buffer. It's also making sure that we have plenty of time for each operation to complete. All right. So I'm going to do Control T right now. This is the decode cycle. So Control T, and this is a really big change, okay? Because the microcode pointer is no longer pointing to location 000 or 001. Where it points to right now depends on the opcode that we are executing. Essentially, whatever the opcode is here is going to be the most significant 8 bits of these 12 bits, and then the least significant, the least significant 4 bits are always going to be zeros, because I want to give myself the leeway of saying, hey, I can specify up to 15 steps for each opcode as microcode in the ROM. So each location in the ROM is called a microcode slice, and it's called microcode because these are used to implement actual opcodes. Opcodes are kind of random. Okay, I could have assigned opcodes in a really random way, which makes the assembler really difficult to write, but that's possible. Okay, on the other hand, the pattern that we store in the ROM is not random, because these are all being used to actually directly control the components of the processor, and that once again includes the multiplexers, demultiplexers, registers, and also the RAM component. So these patterns are not random at all, because they have each bit has a very specific purpose to it. Alright, so now we're going to analyze what components are active and what components are not active, and how things are connected. As I said earlier, on Tuesday, the first thing I usually go to is RAM. Because if RAM is active, it automatically asks 2 additional questions. And we can see RAM is active because the select of RAM is a 1. So now we immediately ask the next 3 questions. I said 2, I lied. There are 3 questions. The first question is, are we reading or writing? Since LD is a 1, we are reading. And then the next question is going to be, who is specifying where we're supposed to be reading in RAM? So now we need to track down port A. It's coming out of a multiplexer. The multiplexer has a select of 1, and that means input 1 of this multiplexer is connected to the A port of RAM. So we need to track down input 1. Input 1 is coming out of the program counter. So once again, the program counter is specifying where in RAM we need to get something. And getting back to column C, this is why we use the dereference operator, and this is also why we are dereferencing the program counter, because the program counter is being used, the value of the program counter is being used as a pointer to get to the location in RAM, and we are not interested in the program counter itself. We're interested in the content of the location in RAM that the program counter is pointing to. So that's why this is a dereference operation. Now, continuing with this analysis, that data line has to go somewhere so that the data is actually utilized. So now we track down the D port and click on it. And this is something you can do in Logisim, because when you click on a node and you're using the POC mode here, it will highlight the entire node. It will basically tell you how it is connected to all of the other components. So right now we already know that the data port connects to the instruction register. Yeah, but the instruction register is not enabled, so it's not going to change anything. And even if we were changed, it's not going to do a single thing, because as long as we are not taking the content out of the instruction register and use it to update the microcode pointer, the instruction register can change all day long and nobody cares. Okay, and let's see where else it's going. It's going into the output of this demultiplexer, which potentially is a bad thing, because if this demultiplexer is also enabled and it wants to output something that is other than the content of what the data port of RAM is trying to output, then we have a bias fight. Fortunately, register output 0 enable is dark green. It is a 0, so this demultiplexer is not even turned on. So it is as if the demultiplexer is not even here. Okay, so it's not a problem. Let's see where else it's going. Okay, so we now track down this multiplexer here. So when you look at this multiplexer, it has an enable, and it is enabled. So maybe we should pay attention, because otherwise, otherwise this multiplexer would not be enabled if there's no purpose to enable it. So RIEN is light green, which means this multiplexer is indeed enabled, and RIMUX, which is connected to the select of this multiplexer, is selecting port 0, input 0. So that's the one that we have highlighted at this point. Oh, okay, so that is going into the register bank. So maybe we need to look into the register bank to see if anything interesting is happening there. Right click, go to view Reg Bank. Do not double click, okay? Because I know someone at this point in this class will still try to double click it, because that's how we expand something for most programs out there. But Logisim is not like that, okay? Double click will open it up, but it's not in the way that we want it, because it would lose the context of how things are actually specified in this particular outermost context. So you want to right click and then select view Reg Bank, and now we're inside the register bank itself. So there's a reason why ones are light green, because we pay attention to those things. So we have this decoder also enabled by this one, because that's also RIEN, which stands for register input enable. So register input enable is a 1. This decoder is enabled, meaning it is actually trying to specify content to its output pins. Okay. And since this is a decoder, it is basically the same thing as a demultiplexer, with the input connected to a constant of 1. Okay, so now the question is, so which output is it trying to drive to a 1 and the other ones are zeros? That is controlled by the select pin. The select pin has 0, 1, which means this is output 0, 0, this is output 0, 1, this is output 1, 0, and this is output 1, 1. And since the select is a 0, 1, so that's why this one is seeing a 1 here, because it is connected to the constant of 1 that is not being shown here. Okay, so what does that do? Well, that turns out to be connected to the enable pin of register B, which means register B is now saying, hey, whenever I see a rising edge at the clock, I'm going to update my value to whatever the D port is telling me. So now we need to track down what D port is connected to. D port is connected to register input, and if you go back to the outside context, this is the same port, and is connected to the multiplexer, which in return connects to the D port of RAM. So it's a very long story, but at this point, the next rising edge is going to update register B to whatever the D port of RAM is specifying. So are you guys still with me? I know this is kind of lengthy and long, but it is not so much the detail that is important. It is how I analyze the operation of the processor that is important. Because if you focus on just the detail, then you learn one thing, which is how the LDI instruction operates. But if you learn the approach, then you can reapply the same approach and go like, okay, I want to see how subtract works. Okay, cool. Kind of the same thing. Okay, I want to see how jump HJMPI works. Kind of the same thing. You will now have the ability to look at any instruction you want to and be able to analyze and go like, oh, I wonder how we can add two values and have the sum to be stored back into one of the registers that we specified for the adding instruction. You can actually do that now. All right. Cool. Yes, your next exam is going to have at least one question that would involve, your knowledge of how the processor works, including, how all of these bits, how all of these tunnels, which are basically outputs coming out of the ROM, how they specify the operations. So sometimes I give you a specific operation and you have to tell me which wire needs to be what. Other times I'll tell you what wire is what, and then I ask you what is it doing. So it can be in either direction. We are in week 8, at the end of week 8 now, if I count correctly. So it's going to be so next week I think I'll give you the practice exam, and then after 1 week after the practice exam I'll give you the actual exam. So I would say we are at least 2 weeks away from exam 2. Okay, so all right, so now that we know what it is going to do, we are going to have a rising edge. Now, there's one reason, there are several reasons, I should say. There are several reasons why register B is brought out as an output pin here. One reason is, I don't have to go into the register bank to see how the registers are getting changed. And the second one is we can use the trace analyzer, and I'll explain how the trace analyzer works. But at this point, we don't have programs that are long enough where the trace analyzer is going to be of any help. But we do want to see the register that in this case, when I have a rising edge, in other words, when the clock goes from 0 to 1, we want to see that register B is going to update to 38 in hexadecimal, which also means in binary, because this is always in binary, it's going to be 0011, which is the 3, and then followed by 1000, which is the 8. Optionally, you can also click on the wire. Now, I have already changed my output to use hexadecimal, for the number that is to the right hand side of the slash. By default, it is a base 10 signed interpretation of the bit pattern, so you can change that. And to change that, you need to go to preferences, I think. And inside, okay, let me pull this in. So inside preferences, you can go to, gosh, I have to remember where that thing is. Not window, layout, yes. Okay, so you have to go to the layout tab, and the last 2 entries specify when you poke on a wire how it is going to display the content or the value on that wire. Binary I'm going to keep, okay, because it is really quite useful when we can look at the individual bits of a multi-bit wire. And then the second one by default is signed decimal. I have changed mine to hexadecimal, and I think it is more useful when it is in hexadecimal. But you can make your choice. I mean, you can change yours anytime you want to. So I'm not going to spend too much time to talk about this. All right. So getting back to the rising edge, right? So Control T on the keyboard gives me a rising edge, and we can see how register B is now in 38. So that's exactly what we wanted to do. Now we are ready to have a falling edge. So the falling edge is going to update the microcode pointer, and the multiplexer that is feeding into the D port of the microcode pointer has a 1 as the selector. So that means input 1 is being used to connect to the output of the multiplexer. So that means we're just incrementing. However, the next location is 2 followed by all zeros, which means the most significant bit coming out of the D port of ROM is going to be a 1. That thing doesn't actually have a name, but we know that it connects to an OR gate, and then the output of the OR gate connects to the reset pin of the microcode pointer, which means for a very, very, very short amount of time, the microcode pointer would actually be 6D1, but then very quickly after that is going to change to all zeros because we are basically resetting it to 0. So when the microcode pointer is reset back to 0 and the clock line is dark green, which cycle are we going back to? I'm just checking to see if anyone is paying attention. Absolutely. Not the rising edge, but it is the fetch cycle. It is the fetch cycle. So we're back to the fetch cycle. Yeah. Control T. Now we're back to the fetch cycle. But guess what? Okay, it's out of view right now. But where do you think the program counter is pointing to now? It was 0, 1. It is now at 0, 2 because when we did when we update register B, it also auto incremented the program counter. That is why when we go to the program counter, it is now at the right location because 0, 2 is where the next instruction is located, and the program counter is now at location 0, 2. I forgot to track it. Okay, that's my fault. I forgot to track the program counter. I was too excited to show you how register B got updated, but when register B got updated, the program counter also updated at the same time to 0, 2. And somebody's going to say, but isn't that a bad thing? Because aren't you kind of pulling the rug under yourself in this situation? The answer is no. The answer is actually no, because even though I am using the location pointed to by the program counter to update register B and updating register B at the same time, remember there are propagational delay to every component, right? So the clock that is used to update the register is updating the register really, really quickly. So it essentially whatever is presented at the D port is being used to update the content of the register immediately. The incrementing of the program counter, on the other hand, is it will take time for the output. Okay, it will take time for the incremented value to update the actual Q port, and then after that it will take time to go through the multiplexer, and then after that it will take even more time for the RAM to respond to the change of the address port. So typically speaking, RAM is very, very slow. Okay, the amount of time it takes to change from the time the address port is changed to the time that the actual location being addressed is changed is long. So that's why in this case we are not really pulling the rug under ourselves, because we understand the delay of various components. We guarantee that we do not have to worry about that problem. So there we go. So now we're going to execute the halt instruction. The halt instruction is interesting in its own way, because it is guaranteed not to move forward, because that's kind of the whole point of halting, right? So we're going to go through the fetch cycle. So this time it's going to be really quick. Control T, we're fetching, and we can see how the instruction register is a 0, 1. Control T again increments the microcode pointer. Doesn't really have a specific name for this particular event. Control T again, we are incrementing the program counter. That's right. So the program counter is still vaguely visible here all the way up here, and so Control T is going to increment it. You can see this as a part of the fetch cycle, like so. And then Control T again, we're going to decode the instruction. In other words, we are going to okay, so somebody's going to say, but the microcode pointer already has 0, 1 in it. Are we done with decoding because the microcode pointer has 0, 0, 1 in it, or this is actually not the result of decoding? What should it be after decoding? After decoding, it is nope. Okay. Remember, we are just left shifting the instruction register by 4 bits, and we're looking at hexadecimal values. So it would be 0, 1, 0. So Daria is correct. Daria is correct. After the decode, the microcode pointer should be 0, 1, 0. So 001 is not is not the result of decoding. This is just incremented from location 000. Decoding is going to decode it. It's going to put a 010 in hexadecimal into the microcode pointer. So I'm going to do Control T right now. Now we have decoded. And you can see, oh, this is really suspicious. Tech, are you really sure that you have initialized this location in ROM? Because it doesn't look like it's initialized. This is exactly what it's supposed to be. Because if you think about it, okay, at least within this version of TTP, all the components are active only if it is enabled or if it is selected. And it is always a 1. That means it is being selected or is being enabled. So if all the bits are zeros coming out of the D port of ROM, that means nothing is updating. Nothing cares about anything. Okay, you can have all the rising edge in the world, nobody cares, right? And then you might say, but what about the falling edge? Because surely the falling edge is going to update the microcode pointer and it's going to move on to the next location, and eventually we'll get to a location that actually does something. Well, for that, we are going to take a look at, let me see. Yeah, so we're going to take a look at what is actually going to be, what the microcode pointer will do on the falling edge. Okay, we are at a rising edge right now, so I'm just going to do a Control T right now because we know none of the other register nor RAM is going to do a single thing because they are all sensitive to a rising edge, but they also need to be enabled to actually do something, and we know nothing is enabled because the ROM is outputting all zeros at this point. So Control T is pretty easy to analyze. Nothing happens. There we go. Now we are doing a falling edge. What do you think this falling edge is going to do? Now this time you want to pay attention to the select of the multiplexer that is feeding the D port of the microcode pointer. So the question once again is, what am I going to do? How am I going to update the microcode pointer at this point? Everything that you need for that analysis is already on the screen. So there's no need to go off screen to look at things because we got everything here. I'm not seeing any answers in the text channel. So let me ask you the question again. We have a falling edge, and what do you think the falling edge is going to do to the microcode pointer? We know none of the other registers are sensitive to a falling edge, so we can forget about the other registers and also RAM. The microcode pointer is the only thing that is sensitive to a falling edge. It is always enabled, which means it's going to be quote-unquote updated. How is it going to be updated? Okay, so I can see that is a guess. Let's not guess, okay? Let's just look at what is presented here. Where do we start? Okay, to answer my question, where do we start? Logically, okay? Logically, where do we start? No, the mux is not disabled. There's no enable to this mux, meaning it's always enabled. We're not resetting because the next location, because it won't even get to the next location. I'll put it that way. It's not even going to get to the next location. Because what makes you think the microcode pointer will increment? It's not going to increment. Okay, so, all right, so let me go through the logic, okay, of how to analyze this. Okay, this is also something that might be important. So for those of you who want to understand how to get something done and not really just the knowledge of this class, you might want to jot down the time, which is 9:46. All right, so to answer the question, let me repeat the question first and then I'll go answer it. The question is, how do you think the microcode pointer is going to update on this, the next falling edge? Because the clock is already a 1, so if I transition again, it's going to be a falling edge, which means the microcode pointer will update The question is, how is it going to be updated? The first thing you do is to track down what connects to the D port, because whenever a register updates, it is just taking a sample of whatever the D port has in order to say, oh, I'm going to make a copy of that to the Q port. Okay, so the first thing to do is to look at the D port. So when we look at the D port, or the node connected to the D port of microcode pointer, it's coming from a multiplexer. So now we have to look at the multiplexer and say, hey, what are you feeding it? How are you feeding the microcode pointer? This mux is always on because it does not have an enable. Okay, this is always enabled. It doesn't have an enable pin. The gray dot marks the selection pin, not the enable pin. So since it's always enabled, we have to look at the selector. The selector is a 0 because it's dark green. So that means input 0 is being used to connect to the output. And what is input 0 of this mux connected to? It's connected to the splitter. And how is this splitter merging bits? Okay, it's making sure the least significant 4 bits are all zeros. But from bit 4 to bit 11, it is connected to the tunnel called instruction, which is the same node, the same tunnel over here. It is coming out of the instruction register. In other words, we are using the 8 bits of the instruction register as bit 4 to bit 11, and then we are just making the constant 0 as bit 0 to bit 3. So that means the microcode pointer is just going to get the instruction register left shifted by 4 bits again. Alright, so technically speaking, it is updated, except that it is updated to the same value that it already has. It's not reset. It is not reset. It just doesn't change. It just doesn't change. The multiplexer is not disabled. It is enabled, but it is connected to the merger. The merger is still connected to the instruction register, which has the same content as before. So it is basically taking the same content from the register, instruction register, left shifted 4 times. Okay, meaning that we are padding the least significant 4 bits with zeros, and then moving everything to the left hand side by 4 bits. And then that is basically the same thing. It's still 0, 1, 0, and we're using 0, 1, 0 to update the microcode pointer, which means it doesn't move at all. Alright, so let me look at the text channel. So the microcode pointer is just getting the same instruction decoded again, okay? Because remember, this process of taking whatever the instruction register has and left shift it 4 times and then stash it into the microcode pointer, that's how we call decoding. But it's decoding the same opcode over and over and over again, so it can never get out of this cycle. Yes, so Richard is correct. The microcode pointer is just getting the same instruction indefinitely at this point, and that's why this is the halt instruction. It stops the program from progressing any further in RAM. It doesn't go any further. It's just stuck at this point. Alright? Do we have any questions about this analysis? Particularly when I ask the question, you always look at the component that I'm asking about, and then you ask, how is this going to be updated? Okay, first of all, is it going to be updated? And then you ask, how is it going to be updated? So if I do a Control T right now, which is the actual falling edge to update the microcode pointer, now look at the content of the microcode pointer. And to quote Doctor Who again, don't blink. Yes, you can blink all you want and it doesn't change a single thing. I was just kidding. So are we good here? Alrighty. As I said, this is just me illustrating how to analyze the execution of instructions. I want you to do this to every single instruction in the opcode table. Now, not all at once, obviously. Okay, that's going to be overwhelming. But do it to the instructions that we have already introduced. Okay, and if you have the curiosity, just pick one up and go like, I wonder how this is done. Okay, and then go through the process. And it is through this process that you get more understanding of how the processor works. I mean, technically speaking, I have explained everything that I can explain, regarding how the processor works and about how each instruction gets its job done. Okay, technically speaking, you already have everything that you need in order to perform your own analysis. So it's really at this time, it's just a matter of doing it. Okay, it's just a matter of just kind of spend the time. Okay, bite the bullet. Sit down and just say, I'm gonna tackle this LD instruction. Okay, there's a difference between an LDI versus the LD instruction. So I didn't do it with the LD instruction, so you have to do it yourself. Okay, because I want to at least leave something for you guys to do. If I explain every single one, then you go like, oh, since Tech has already explained it, I don't have to do my own exercise. And then by the time we get to exam 2, and you have to actually look at all these bits, all the zeros and ones, and go like, I have no idea how to do this. But if you were to do this like constantly, after every class, you pick an instruction and go like, I'm gonna pick on this one, and I'll find out how it works. And by the time you get to exam 2, you already have this process down. Okay, you know exactly how to analyze the operation of the entire processor. So that is kind of what I want you guys to do. All right. Yeah, well, that's the reason why everything is being recorded. In fact, you can watch the one from last semester, and then the semester before that, and then the semester before that. I explain the same thing slightly differently every semester, even though it's really the same processor. It has been the same for, I would say, about at least a year or two. So you can kind of dig back into the older lectures if you want to. All right. So let me take a look at the time. It's 53. I don't think I'm going to take row today. So for those of you who are thinking, hey, if you're not taking row, I'm going to take off, I'm not going to stop you. But for the rest of the class, we're going to continue with our discussion. Cool. Right. Yeah, well, I mean, I don't mean anyone in this class is going to do that, but I have seen people like that. The moment I mention, I'm not going to take row today, poof, gone. All right, so what we're going to do now is to say, we need to write programs in this particular fashion. That's going to be super tedious, right? Because, and we don't know how to get to the specific locations, okay? Because okay, let me just kind of illustrate what I want to do. Okay. So let's just say that I want to okay, I'm going to write the program here. Okay, I want to write a program that increments the value of a memory location and initialize it first. Okay, so we'll say initialize the value of a memory location to 0, and then increment the value of a location, same location, and let's just say this is all we want to do. The question is, how are we going to do this? So we have introduced a few instructions, but there are some instructions that we haven't introduced yet. So you're going to say, it seems to have to do, okay, it has to do with memory locations, right? So in order to store something into memory location, there's only one instruction that can do it. So when you go back to the opcode table and you look through column C, there's only one instruction here that has asterisk something on the left-hand side of the assignment. So let's go through this list and find out which one it is. Okay, we actually talked about it already, but just pretend that we have not. Okay, so PC is on the left-hand side, but there's no asterisk. And we look through all of these things, no asterisk on the, no dereferencing on the left-hand side of the assignment, until we get to Here. Oh, okay. So the ST instruction is the only way to store something into a memory location. Okay, fine. We'll put it into the just imagine you have a little tray, that will contain all the tools and all the supplies that you need to do something. So you're putting the ST instruction into that tray. Okay, we're just reminding ourselves, this is one of the things we definitely need to do. Okay, next. Well, since we need to specify a memory location, so we need to somehow get it into a register. Because if you look at this instruction here, do you think I can specify where I want to store the content to, without the use of any additional instructions? It is a pointer, but it's not initialized. It can only use registers for Y, and it can only use registers for X, which means it cannot use a constant for Y, it cannot use a constant for X. So how am I supposed to specify where I'm supposed to initialize to 0? With just the ST instruction, I cannot, okay? Because I need to initialize a register first. Specifically, whatever register Y turns out that I choose to use, that register needs to be initialized first. Does that make sense? Because Y has to be a register. Okay, all right. All right, so how do I initialize a register? How do I put a very specific value into a register? We just talked about it today. LDI, very good. Okay, so we're going to put LDI into our little tray of parts that we need. Okay, very good. So with ST and LDI, I would be able to initialize a specific memory location to 0. Okay, and I'm going to put a specific, so I'm going to have to say, okay, that location, not just any location, that location. All right. And we need to increment the value of that same memory location. So increment means we have to read it back and then store the incremented value. Yes, I know we just initialized it, but assuming that we are not doing that kind of optimization, increment means we have to read back the content of that location, then add 1 to it, and then store it back to that location. So now we need a way to read the content of a specific memory location. So now we are looking for dereferencing on the right hand side of the assignment, and there are plenty, right? So this one is reading, this one is reading, this one is yes, they're all dereferencing the program counter, but we don't want to update the program counter itself, okay? Because whatever we are reading into has to be something that we can add 1 specifically in software. That means we have to be reading the content of that memory location into a register, into one of the 4 registers in the register bank. So that means we're looking for either X or Y on the left hand side of the assignment. This one has X in it, but it doesn't. This one is just X equals Y. So in other words, we're just copying the content of one register to another register, which is not what we want, because we want the memory location. We want the content at a memory location to be copied to a register. So we are looking for dereference on the right hand side and a register without dereference on the left hand side of the assignment. So this is not going to do the trick. These are not using registers. This one, this one does not actually do the trick, because whatever we are dereferencing on the right hand side is just the program counter. I have no control and say, that register over there is already initialized to the address where we want to go. Let's use that register for dereferencing. Nope, this one is always just going to use the program counter. So not going to help us, right? This one, on the other hand, fits the bill, because this one says we can now choose, okay, which register we want to use as a pointer on the right hand side to dereference, so that we can get the value of a memory location. And we can also choose which register on the left hand side of the assignment, so that register gets updated. This is the LD instruction, which is the opposite of the ST instruction. Alright, so we'll put it into our bin here. Okay, so we need an LD instruction. And then we need to increment. Okay, so increment is relatively easy because we got one increment instruction here somewhere, which is just, register plus plus. Okay, so we'll check out which one it is. There we go, plus plus register, increment x. Okay, so we can use increment in order to increase the value of a register by 1. And then after that register increments by 1, we need another ST instruction, but it's already in the tray, but we need it one more time, so we're going to put ST here. And that should complete the entire operation. Okay, so as the last thing we want to do is to halt, basically just to say this is the end of the entire program, don't proceed any further. Alright, so now that we know we need all of these individual parts, we still need to specify a place so that place is where we want the initialization to go. In other words, we need to specify a specific memory location. Now, after these, remember, this is a von Neumann architecture, which means memory is used, RAM is used to store both the data, in this case, the location that is being initialized to 0, and also to be incremented. So and it's also used for instructions. And we have to make sure that we don't accidentally overwrite the instructions, because that would be very bad. Okay. So now we're going to say, maybe the next instruction here, whatever byte is here, is going to be our specific memory location to be initialized to 0 and then incremented once. Okay. All right. So how do we get to this address here? So now you have to first sequence everything first, okay? Because now we have to say, we can't really do a ST first because we need an LDI instruction in order to specify the exact content of a register first. So we'll pick register A for this purpose, but we have no idea where in memory, is this location here. So we can only put a question mark here to be resolved later, okay? And then we say, we want to put a 0 into that location. But once again, 0 is a constant. ST cannot use a constant for the Y nor the X. Okay, Y has to be a register, X also has to be a register. In other words, we have to initialize another register to be 0 so that that register can now specify that we want to initialize the location that we want to initialize with a value of 0. Okay, so we're going to use another LDI instruction, LDI B with a 0. Okay, so this way, after this, register A has the address, register B has the value. Now we can use the ST instruction. So we can say, let's store to the location that register A is pointing to, and the value that we're going to store at that location is whatever value is currently in register B. Are you guys still following me? All right, excellent. Sort of. Okay, so maybe when you watch this again and kind of do it slower, a little bit slower, you'll be able to kind of digest the various steps and the reasoning, the rationale of what I'm doing here. That is kind of important. All right, it is a lot. It is a lot. Okay, so now that we have okay, so if you want to, okay, I can even comment this program, right? So this is the same thing as saying, okay, let's do an assignment. Register A, is some value that we'll determine later, and then B is getting 0, and then this time, whatever register A is pointing to is going to get the value of register B, but we know register B just has a 0 in it, and register A has this question mark in it. So effectively speaking, okay, this one is really doing the same thing as, let's dereference whatever the question marks are and store a 0 into that location. Okay, next we need to increment. So as I said a little bit earlier, increment usually needs to do an LD first. So we're going to use an LD. The location we want to read it from is still in register A, so we can just keep register A the way it is. Register B is not useful anymore, so we can actually overwrite register B. So we are doing this. So B is whatever register A has. And then we want to increment B, which is the value at the location that we are interested in. And then we have to store it back to that same location. And then we have a halt instruction here. So if I were to comment everything here, so b is b plus 1, okay, b increments, but b needs to be stored back into whatever a is pointing to, because the objective is not to increment a register, the objective is to increment the content of a memory location. The reason is simple. We only got 4 registers, okay, but we have 256 memory locations. So it would not make any sense to try to put all the data that we have to track in the registers. We want to put all of that stuff into the memory content. The registers are useful, okay, but we don't want to keep too much stuff in the registers all the time because we only got 4 of them. All right. So now, can we get to this location? Can we get to this, question mark, question mark, question mark here? The answer is yes, we can, but it's going to be some tedious counting because we need to know, okay, we know this LDI instruction is going to be at location 0, but it's going to take up 2 bytes, right? So LDI is going to take up bytes 0 and 1. Another LDI instruction is going to take up locations 2 and 3. This is going to be at location 4 because ST only needs 1 single byte. And then we have another LD instruction which takes only 1 byte, so that would be location 5. This is location 6 because increment also takes just 1 byte. And this is location 7 because it also takes 1 byte. Increment takes 1 byte. And then this also only takes 1 byte, but I have lost track already. Let's do the counting again. 0, 1, 2, 3, 4, 5, 6, 7, 8. So that means this is at location 9. Okay, so this is me doing the assembling by hand. Okay, and you go like, Tech, you are a tool person. Surely you have, you have some tools so that you don't have to do all this counting here. Saying, oh, this instruction is going to take up 2 bytes, this one's going to take up 2 bytes, this one's going to take up 1 byte, and then we just have to add them all to get to this location here. This is location 9, at least according to my calculation, right? So the idea is, let's use labels, okay? Because what a label is just a symbolic name. Okay, so we're going to use a label here. I'm going to call this label L1, which is an awful name for a label, but it's okay. And we're going to say, let's reserve 1 byte here and initialize it to 0. That's what byte 0 is doing, is telling the assembler and say, we're going to use this byte for something, and let's initialize this byte to a 0. Now, just because we put a 0 here doesn't mean that we should not be initializing in our code, because this code here to do the initialization can be in a loop. In other words, it can be after some code that has already changed the original value of this byte from 0 to something else. So we want to use runtime code to initialize a location when we are not really sure whether some other code might have changed that location already. All right, so what is this label doing? Okay, well, the nice thing about this label is now I can use the name, I can use a reference to the label name over here. So this way I don't have to go back and say, okay, that location is 9 because according to my counting, that's where I need to place the 1 byte that I want to initialize to 0 first and then increment by 1. I can now just say, that location has a symbolic name of L1. So L1, this is a reference to label L1, and this is the definition of label L1. The definition has a colon after the label itself. So I'm going to pause here, let you guys ask questions, and then we're going to assemble this program, let it run, and see that it actually gets the job done. Alright, so Richard said, just to make sure I'm understanding this, label L1 colon is a symbolic name for a location in RAM. Yes, so in this case it is. Labels can also be used for other things, but this is the simplest use of a label, which is basically just saying, hey, whatever this location is, let's call that L1. Jonathan is asking, oh, okay, Colton first. TDP processes output from top to bottom. The assembler does, not the processor. The processor reads from location 0 first to determine what opcode it is going to execute first. And then from that point, it's going to execute sequentially until we get to some kind of jump instruction. And then Jonathan asked, why did we switch question mark, question mark, question mark with L1? Because the question mark is representing where do we want to put that byte that is supposed to be initialized to 0 and then incremented to 1. Now that we have used the label and also byte 0 to specify where that byte is supposed to be, I don't need to count anymore and put in the literal constant of 9. I can now let the assembler do all the counting and say, hey, assembler, when you're done counting, just tell me what label L1 is supposed to be, and I'm just going to put a reference of label L1 over here. Yeah. Next is Matt. Couldn't we utilize the binary of hexadecimal information to try to figure out what the location would be? Yes, we can. It's just very tedious. Okay, so these are all terrific questions. And then Colton is asking, why is byte 0 not at the same location as A? Because A refers to a register, 0, location 0, the location containing byte 0 is in RAM. They are entirely different things. One is inside the processor, one is outside of the processor. One is inside the register bank inside the processor, the other one is a location in RAM. Alright. Okay, we got a few more text coming in, but I am going to proceed to use the assembler, because now I'm going to say it's too much trouble to try to come up with the bytes for this particular program. I'm going to use the assembler because, after all, that is what the assembler is for. So A is at location 1. No. A is a register. It is not at a memory location. Registers are not in memory. If you look at the logisim, you can see how they are different things. Right? RAM is RAM, and then the registers A, B, C, and D are within the register bank, which is a part of the processor itself. Alrighty. Okay, so let's go to the source here, and we're going to specify our program. So I'm just going to type it in. Now you can type it in, or you can just kind of copy and paste from a text editor. Let me just kind of type it in the way it is. Okay, and I'm going to specify 9 here first, because I want to see if I am actually right. So LDIB with a 0, STAB, and then LDBA, increment B, STAB again, and then the halt instruction, and then the byte 0 here. So the byte 0 is still needed here, because if you have any additional code that you want to specify after the byte 0, you can do it here. Okay, there's no reason in this particular architecture and assembler, there's no reason why you cannot interleave code and data. So the instructions and the locations where and the locations that you use to store the data, they can kind of interleave as long as you're not interrupting the sequence of instructions. Alright, so we got 2 more people typing, but I'm going to go to the Assemble tab, because the Assemble tab is actually one of the most useful tabs of the entire assembler, because it shows you what the assembler, where the assembler is putting everything into RAM. And then Colton said, oh, so the value provided to register A is not a literal value, but the value of the content at a location. The content at a location. Okay, so at this point I just verify one thing. It is at location 9, because remember, column V and column W, one is in decimal, column V is decimal, column W is in hexadecimal. That is specifying the address, and then column X and Y specifies what content would go to those locations. So we can see how 09, the address, is corresponding to byte 0, which means I actually did count correctly. It is at location 9. But the chances that I would do some counting correctly, I would do the counting correctly in a simple program, even a simple program, is pretty rare. Okay, so it is not a good idea to rely on me doing all the tedious counting. So now I'm going to go back to the source code and change so that we have a label. So I have to put in a label definition here, and then put byte 0 down here, and then I'm going to change the first LDI instruction. Instead of putting a 9 here, I use L1. I refer to label L1 here. Alright, so in the text channel, on the opcode table, why does ST have parentheses for Y in STYX? Because I'm trying to use the syntactic structure of parentheses to make it more visible that we are dereferencing Y. I could have used the asterisk symbol, but it is more conventional in assembly language to use parentheses to emphasize that we are dereferencing. Yep, there we go. Okay, and then Colton wrote, so using label L1 is simply to simplify and better organize one's input for the registers. No, not input. It is just a location. Label L1 is simply, in this case, the symbolic name of the location of this byte 0. Now you can use a label to label the location of an instruction. That's fine too, and in fact that is very useful when we get to conditional statements and loops. But we're not there yet, so I'm not concerned about that. Okay, now that I've changed the source code, let's go back to the assemble tab and see if the program has changed. And the answer is no, the program has not changed. And it would even tell us that label L1 is defined to be 9. This is basically how you read row 8 of the spreadsheet. Is label L1 is defined to be 9. Now there's another tab here that you can use to find out how each label is defined. So if you scroll to Sim tab, which is symbol table, it will give you the JSON format, the JSON or JavaScript object or notation format of how labels are defined. So in this case, label L1, which is defined on line 7, has a RPN or reverse Polish notation of a constant of 9. So don't worry about what is a RPN or reverse Polish notation. Not yet. Okay, we'll get to that later. But it simply means that it is a constant of 9. So it is defined on line 7. It is defined to a value of 9. And there's no error associated with this particular definition. It's 0 oriented. That's why. I think. Yes, I'm the one who wrote the code, but I have to. Yeah, so it's actually row 8, but it's actually, since we count from 0 when we are doing programming, so that's why it says it's 7, because it is 0 oriented when we look at the quote-unquote line number in the JSON format. There we go. Okay, so. Let's see. Let's take a look at the time. It's 10:18. We have enough to start the lab today. So I'm gonna release the lab, which I think has a passcode. So we'll talk about the passcode, and then you guys can work on today's lab. All right. Where is that? Right here. Okay. So we are gonna work on the lab that uses LD, ST, and LDI. That's why I chose those instructions to talk about on Tuesday and also today. So let me go change this so that we specify a due date, which is 1:20 p.m. today. And we can get started. All right. So the passcode is just LDI. I'm going to put it into the text channel. LDI is the passcode of the lab, and it's due at 1:20 p.m. like so, and then save and publish. There we go. Now, after you're done with this lab, okay, you have like 5 days before we have class next Tuesday again. So I want you guys to, there's not a whole lot of reading material anymore. Okay, it is all about, okay, let me back up a little bit. When I said there's no reading material, I mean this is your reading material, because the design of the processor is completely self-documented, and we have explained how each component works. So, and I have also explained how we analyze the processor so that we can figure out how something is done, when we specify a particular instruction. That is why there's no reading material anymore, because it is all in the processor design in LogiSim. The other part of the reading material, okay, there is some reading material, but it's not in the form of a module. Opcode table is part of the reading material because this, particularly column C, is really useful. Column B allows you to use the assembler, and then column A allows you to hand assemble, instructions if you want to. But column C is super important because you should be able to analyze the processor, analyze all the multiplexers and all the registers and whatnot, and confirm that column C is describing what is going on in the processor when you execute specific opcodes. And then the other part, there's one more part here. Where is it? I'm going to open up Google Drive again. It's the assembler manual. Okay, the assembler manual is also really useful. It is available to you, and unless you're one of those people who do not like to read the manual before you use a particular thing, and I have to confess that I'm one of those people. I usually do it that way until I run up against something that I don't know how to do, and then go like, okay, it's time to open up the manual. Usually not when I'm dealing with something dangerous, okay? Usually only when I'm dealing with something that is not so dangerous, like assembling furnitures. Sometimes I have to disassemble the furniture a whole lot just to get back to the part where I missed something, or install something backwards. Happened in the past? Okay, this is the assembler manual. So the few items that are now the reading material would be the processor itself in LogiSim, the assembler manual, which is this document here, and then the opcode table. So these are basically between these three documents, okay? You really have everything that you need to understand how the processor works. Now, what we're going to talk about in the near future is how do we combine the instructions into larger units, and then how do we translate C code into assembler code. Now that would be something new, and there are written modules for that purpose. But at this point, we are much more just focused on how things happen inside the processor. Alright, so we got a few text messages coming up. Do column B to U have applications for us? And I'm assuming Colton is referring to the assembler. The answer is not in general. Okay, so when you look at the assembler, there's a reason why I hid all of those columns. Now, for those of you who are curious, you can actually, okay, this part is optional. So the assembler itself is open sourced. In other words, you can actually go to every single cell, look at the equations, okay, and figure out how it gets something done. Now I use array formula a lot, which means you have to go to row 1 to actually look at the equation being used in order to implement the assembler. So in that sense, the assembler itself is also open source, but you don't need to read it. Okay, for those of you who are super curious and you have too much time on your hand, go ahead. But for the rest of the class, just use it as a tool. You don't need to understand how the tool operates. Okay, but column V, W, X, Y of the assemble tab can be extremely helpful when you're trying to understand how the assembler works, because it gives you a correspondence between the source code and the byte that it assembles into. So that means it can be very helpful. The RAM file, on the other hand, is just the output that you can download, and you can put it into the RAM component when you run the code inside LogiSim. So that's the only purpose of the RAM file tab, is to give you a file that is formatted in a way that LogiSim can take in as input, so that you can just kind of load it into the RAM component and run your code. That's the purpose of the RAM tab, RAM file tab. Okay, so do we have any additional questions? I see a bunch of direct messages, but I'm not sure how many of those are coming from this class. If there are no questions, I'm gonna stop the live stream and also the screen share. Okay, we got one confirmation that we are good. All right. Does anyone want me to kind of illustrate how to put an assembled program into the RAM component? Okay. Yeah, I illustrated that the other day, but I'm going to do it again. So you have to go, make sure you're at the RAM file tab, and then you go to File, and then you go to Download, and then you choose CSV, comma separate the value, and then you make sure that you remember where you put that file. Okay, I typically want to just save file. I don't want to open it, and I'll stash it to a location and give it a specific name. Okay, so in this case, I'll give it a name of test1. Okay, test1.csv in the temp folder. And then when you switch to Logisim, oh, I just passed it. There you go. So when I go to Logisim, now if you want to make sure that you have a fresh Logisim and it's not a continuation of some program that you have run already, you can go to Simulate and then you can reset it. So when you reset simulation, it will also reset the content of RAM. But that's okay because the program you're dealing with right now are fairly short and it's pretty easy to load the content of RAM again. So right click on the RAM component, go to Load Image, and then point this to where you saved the file earlier. So in my case, it's in my temp folder, and the name is test1.csv. So this is typically alphabetically sorted. This is test1.csv. Open the file, and now we have all the content inside RAM. And assuming the program has a halt instruction at the very end, typically for what we're doing at this point, okay, at least for the lab, now when you're trying to investigate how each instruction works, you don't want to do it this way, okay? But for the lab, where sometimes I just ask, what is in this register at the end of the execution of this program, okay? If that was the question, then you can just kind of simulate at full speed, which means you enable ticks automatically, and now it's done. Now how do we know it's done? Because the halt pin is a 1. So at that point you can stop the ticking. Okay, you don't have to, but you can stop it. And then you can, usually I ask what is in a particular register, maybe the program counter register, maybe one of the 4 registers from the register bank. So if the question is asking what is in register A in hexadecimal, then you just poke on this wire, make sure that the output is in hexadecimal and not in signed decimal. And then 09 would be the answer to that hypothetical question. So are we good? Are we good here? I mean, that's basically the process. I believe the lab also includes the instruction of how to do that, but just want to illustrate it one more time, just so that you guys can get to it quicker. All right. So if there's nothing else, I'm going to stop the live stream and also the screen share, and then I'll stay online to answer questions. And I got a few people